So let's now iterate a little bit about the expression of the constitutive equation. We are repeating something which is pretty similar to what we did already in elastic solids. But considering that now, on top of this term, which resembles very much the one that we had in solids, we have this term. Again, what we did. Maybe you can remember that we consider that, as we always can do, we can split the stresses into the spherical part and the deviatoric part. And the definition of the spherical part is minus the mean pressure times the identity. Okay? And what is the relation of the mean pressure with respect to the trace of D, which is the divergence of B? That one. We already got that. So, there is the relation of the spherical part of the stress tensor characterized by the mean pressure and some velocity scalar measure is that the mean pressure equal to the thermodynamic pressure minus K trace of D. That's an interview of time. What about the rest? What about the deviatoric part of the stress tensor? Well, it's a matter of operation. Just we consider that. We just split the stresses into the spherical part and the deviatoric part. We isolate the deviatoric part. We just pass this term to the other side. We obtain that. We replace that equation into here. We just make some additional operation. And then we realize, curious enough, that the deviatoric part of the stresses and the deviatoric part of the rate of the strains are related one-to-one with the factor 2 mu. By the way, maybe you remember that in elasticity it was also the same. We related, you maybe remember, the deviatoric stresses and the deviatoric strains as the factor 2 mu. And this is the same, with the only difference that in terms of having here the deviatoric strains, we have that deviatoric rate of strains. And look, in this equation, the thermodynamic pressure doesn't play any role. So look, and it's important, the deviatoric part of the stresses depend only on the deviatoric part of the rate of the strains through the viscosity. That viscosity, not mu but lambda, not lambda but mu. And of course, whenever mu is equal to 0, we have no deviatoric rate of the strains. So the only part that exists in the case of mu equals 0 is the spherical part of the strains, which is not that. Is that plus is that. The spherical part of the stresses are the one coming out from the thermodynamic pressure here, plus the one coming out for the trace, the term here. Okay? Well, so this is the summary of that. For one hand, we can split what happens for the full stress relationship of stresses with rate of strains into one that refers to the spherical part, the mean pressure, which depends on trace of D. Look, initially, for no velocity, there is, for the case trace of D equal to 0, we have something which is a pressure, that then, the mean pressure, which is the thermodynamic pressure, and then as we increase the velocity, that term is to be positive, so we have a small variation, a negative variation of the mean pressure. Okay? But for the deviatoric part, every component, sigma 1, sigma prime 1, for instance, is proportional to D prime 1. Sigma 1, 3, sigma prime 1, 3 is proportional to D prime 1, 3. But the only point, and that's the difference, that now the coefficient of proportionality 2 mu that in elasticity was constant, here will depend, can depend even from the values of D. So it's a second proportionality factor rather than a tangent proportionality factor.